I'll begin with a word of prayer. Dearly Father, we thank you for this day, and I just pray you bless this class. Help us to just use this time wisely, Lord. In your name I pray. Amen. So I promised I would rant and rave about the test. I mean, I guess the ranting and raving I wasn't promising, but I will do my best to be. How dare you? Do better. There. No, I mean, you guys are still learning this stuff, so people make mistakes. But I think we all have room to improve, me included. Turn off the lights in the front here. So I didn't think problem 1 was going to be a trick question, but some people found it tricky. So like, I don't know. I think there's a lot of people who have a mental block over realizing 0. 0 is a rational number, right? But 0 also serves as the additive identity for real numbers. So if you have a set which doesn't have 0 in it, it can't be an additive subgroup of real numbers. So that's it. 0 is in Q, so it's not in this. This G is just a fancy, this is just the irrational numbers, right? Numbers which are not rational. Now some people, I was also perfectly happy with people who told me like 1 plus root 2 plus minus root 2 is 1. 1 is rational, but it's not in G, so it's not closed under addition. I mean, this is not the only argument, but something like that. Some people just said it's not closed under addition. Well, that's great, but if you don't show me a specific thing where that happens, I'm going to take a point off or maybe more. You know, you can't just, you have to give evidence for your claims. This one here, I think we had a lot of success on this one. You should be happy. I took about a half a minute looking through my brother's webpage. You know, he's got the Euclidean algorithm thing, and I stayed with 101, and I picked different numbers until I found 76 had just a 3 or 2 step Euclidean algorithm. So I chose that one for the test. I was trying to be nice. So as you can see, it's relatively easy to find that, and yet not entire. It's easy, and yet it's. I don't think it's at all obvious that 4 is the multiplicative inverse of 76 mod 101 either, right? I mean, I really like this example. It's calculationally easy, but if you don't know this, so by and large, you guys did this well. I had one person do, instead of division algorithm, they did the subtraction algorithm. That makes this harder. Remember when we first teach division algorithm, we'll show you by repeated subtraction you can do it? Never mind. Anyway, x equals 100. Any questions? I'm going to try to go on then. I think this should have been a very popular question on the test. It's like, thank you, finally throwing me a bone. Yeah, I think some people managed to get 3s in here somehow. I don't know how that happened, but if I saw a 3, I kind of knew something was up. And let's see here. So find each unit of Z mod 9, which generates all of, the multiplicative group mod 9, the group of units mod 9, if you like. In Galilean, he just uses U9 for this. If you look at my stuff from last year, you'll find this called U9. You guys probably already knew this, but if you look at my stuff from last year, that's the translation. Anyway, so it's fairly easy to see that. I mean, how I did this was I just picked a number and saw what happened. So the first thing I saw to pick was 2, and I calculated powers of 2, and I saw that it took me till the 6th power to get back to 1, which tells me that the cyclic subgroup generated by 2 is order 6, but that's everything. So 2 is a generator. And then we have a theorem which says that if you want to get another generator, you can just take the, how to say this? So since Z mod 9, for the purpose of me talking, U9 has 6 things in it. The group of units mod 6, which are 1 and 5. So 2 to the 1 will be another generator, and 2 to the 5 will be another generator. This is one of the theorems we had in the cyclic group, cyclic section. Trying to remember the, how'd it go? Trying to remember. G to the, oh man, I can't remember. Just a second. There's a nice formula to write down here. Where's that stupid thing? Here it is. It's theorem 8 from this. There's another way to write this that I'm remembering, but I can't quite find the words at the moment. So anyway, this is equal to that if and only if, let's just say G. And let's suppose that the order of G is n if and only if the greatest common divisor of k and n is 1. But what that means, right, this basically means that k is an element of, one of these guys, So since I'm looking at a group of order 6, once I found one generator, I know that the 5th power of that will also be a generator. Excuse me. Sorry about that. If I was working in a group of order 19, and if I knew that G was equal to this, right, good news. This is equal to G to the K for K equals to what? 1, 2, 3, 4, 5, 18. Because Z19 star is everything. Okay. So that I don't think you guys knew that. A lot of people did not have a clear understanding of how to get other generators. Like once you have one generator for a cyclic group, how do you get other generators? Theorem 8 told us that. Find elements in Z90 with order 9. So 90 divided by 9 gives me 10. I'm using yet another theorem in the cyclic groups chapter, cyclic groups section. So 90 over 9 equals 10. And then again, I already know how to get other generators because I just have the group of units. I have Z9 stars right up here. So anything in there times 10 gives me another generator. Same idea again. How do you get new generators from old? Have to look at relatively prime multiples or relatively prime powers to the group that we're generating. And so that gives me 10, 20, 40, 50, 70, 80, which of course I'm sure some of you just calculated by direct just figuring. I could tell from the scribbling. But this is how we should do it. And of course, I could easily ask this question, both of these questions, in sort of a more abstract sense. I could tell you, suppose you're working with a group of order blah, you have an element of order blah. How do you, what other generators would be given for the subgroup which that generates? And so you'd be out, you could be outside the context of Z90, and then you'd kind of be up a creek if you were just thinking in terms of just raw calculation, like some of you were. Okay, enough. This I did in the review, right? This is why it's on test 1, because this is meant to be a gift. And a lot of you got this, give or take. But you should, at some point in the proof, you should explain where you're using surjectivity, right? At some point in the proof, you should explain where you're using that G is abelian, right? At some point in the proof, you probably should mention that you're using the homomorphism property. These are things I like to see. Any questions about this one? Okay. You should not have phi inverse in this proof because there is no phi inverse necessarily. Problem 7. This is a major theorem that we went over in class. Everybody should be ready for this one. Most people butchered the, let's see which direction. not the last part. The conversely part, everybody's fine with. If n divides k, then there exists j such that k is equal to nj, so x to the k is x to the nj, which is x to the n to the j, which is 1 to the j, which is 1. Like, everybody got this direction. Woohoo! Which is good. That's a thing. But the other direction, so much wrongness. So suppose x to the k equals 1, all right? Then that, by the division algorithm, there exists r and q such that k is equal to qn plus r, right? Where this r is between 0 and n. Hence, x to the k is x to the qn plus r, which is, we can, by laws of exponents, do that. And so, of course, since x has, come on, I got to get new batteries in this thing. X to the n has, that's 1. So we get x to the r. So x to the k is equal to 1, which means x to the r is equal to 1, but r is less than n. Therefore, r has to be 0 because we said x has order n, right? So by the definition of order n, that must be 0, which then tells you that k is equal to qn, which shows that n divides k. The mistake that I saw, I don't know, half the class make, something like this. Basically, it comes down to something like this. You got x to the a, you got x to the b. Let's get to the point here. You got x to the a plus b, or no, sorry. You got x to the ab is equal to x to the c, and then you guys are like, so that implies that ab equals to c. I mean, I saw this error in many different guises, but it's this error. You assume laws of exponents hold for a group. They do not. This implication is simply not true. I mean, you pick your favorite group. How about this? How about 2 to the 3 times 5 equals to 2 to the, I don't know. Let's see here. 2 to the 1. In, would this be true? I should at least give you something that's true before I'm sorry, I have to come up with a example, counterexample to this thing here for a second. Maybe you guys are thinking more clearly than I am at the moment. Maybe you can come up with an example for me. How about this? I'll work in, let me pick my modulus. Let's work in Z5. So let's see here. 3 to the 2 times 3 is equal to what? 3 to the 6th, right? Which is what, mod 5? Right? 3 to the 3 plus 3 plus 3 is 6, which is 27 times 27, which is 2 times 2, which is equal to 4. Now I need to rewrite that as a power of 3. 4 is equal to what power of 3 mod 5? Help me out. I'm not doing this a very smart way. 3 squared? All right, so that's a great example. So this is my A, this is my B, this is my C. So what the class is telling me is that 2 times 3 is equal to 2. What's that? Oh, right. It's not even true mod 5, right? Yeah, it's not even that. It's not even a question of the modulus also extends to exponents. No, and that is not the case. I don't think it does. So this just isn't true, all right? That is not true for groups, generally speaking, right? I mean, you can say this much. If we have x to the ab minus c equals to 1, what's that tell us? That tells us that ab minus c is a multiple of the order of x, right? So if x has finite order, that means that AB minus C is a multiple of whatever that order is. But even that you shouldn't assume, because the point of this problem is to prove that. So even assuming laws of exponents in that context is still circular reasoning and bad. You have to work from base principles on this problem to give a proper solution. I hope I made my point. Problem 8. Sorry about this problem. There are elements to this problem which are still worthy. The thing that was completely unfair to you guys was this piece right here, counting distinct subgroups. The theorem we have for counting distinct subgroups was for cyclic groups. Yeah, so I'm trying to think here. Well, anyway, if you look at the homework problem I gave you, it was on like z something cross z something, right? So in that context, that logic worked. But here, because of the dihedral group, this is a non-abelian group, and the structure of subgroups is just more complicated than that homework problem. So you actually would have to get into details to figure out how many subgroups there are. I have a somewhat educated friend who thinks there are 17, but I haven't checked it myself. We did agree, though, and you guys could have figured this out, that there are 64 elements of order 10. But my educated friend also says that that's not an interesting question because it's just ugly combinatorics. Now, whether or not you think that's ugly probably has to do with whether or not you think combinatorics is interesting, right? Like if you ask Dr. Sprano if this is an interesting problem, he'd be like, yes, this is a very interesting problem because Dr. Sprano, did I say Scambortis? Should not confuse these two. Because Dr. Sprano, of course, loves combinatorics, but I've heard him more than once say he'd love to teach a course in combinatorics, you know, which of course we don't have. But anyway, so if you look at it, to get the order to be 10, we need the least common multiple of the orders to be 10, right? So the question is, how can that happen? If we're picking elements from Z10 to get order 10, well, any generator of Z10 will do. So the Euler phi function tells me there are 4 choices there. On the other hand, for D5, there is no element of order 10, right? But there are elements of order 1, 5, and 2. So one way I can get least common multiple be 10 is to have this 10 and have this be any divisor of 10, right? That's one way. 4 choices here. There's 1 element of 1. There's actually 4 elements of order 5. And there are 5 elements of order 2 in D5. We talked about that in class a fair amount. And so that gives you 10, 4 times 10, 40 choices here. We could also have 5 times 2. That would give me a least common multiple of 10, right? There are 4 choices for A being order 5. There are 5 choices for B having order 2 because we're talking about D5. So you've got any of the reflections in D5 are of order 2. Y, yx, yx squared, yx cubed, yx to the 4th, all order 2. And then here's what I forgot in my first attempt at the solution. There's a third case, which is we could have that be 2, that be 5. That also gives us the least common multiple of 10. And of course there are, excuse me, one of these in Z10. There's only one element of order 2 in Z10, namely 5. And there are, again, 4 elements of order 5 in D5. X, x squared, x cubed, x to the 4th, these all have order 5 in D5. So that gives me another 4 choices. So in total, there are 64 elements of order 10. Yeah.
A whole bunch more elements in D5 that are of order 2.
Why?
Isn't it like the 5 ones with y as well as x to the 4th?
Well,
Oh, no, it's just those 5.
yeah. Now, if it was D6, then there'd be 7. Yeah. But if it's an odd n, then there's just half of it has order 2. If it's even, then half plus 1 have order 2. Yeah. One of the things I'm hoping to prove Friday is a beautiful application of Lagrange's theorem is that If we look at a group of order 2p where p is a prime, then it's either cyclic or it has to be dp. And I don't know, so the dihedral group is kind of an important example. It comes up all over the place. I'm sorry, that has nothing to do with what we're doing at the moment. I'm excited about proving it. So I'll shut up. This was not meant to be a hard problem. And a lot of you got it, I think, completely. So one thing that's challenging about this problem is I'm testing to see if you know the definition of the center. If you don't know that, you're kind of up a creek. But the center of a group is a set of all elements which commute with the whole group, right? And so 1 is in there. If I pick A and B in the center, then you can see that for any G and G, we have that AB commutes with G, right? And I was very happy if you guys wrote down associativity and stuff. I'm just being lazy in my solution a little bit. My apologies. It's better if you wrote associative there. Don't give up on that kind of detail. It's good. Of course, do budget your time. But, yeah, shut up. So that means AB is in there, so ZG is the center is closed. And then I showed you guys this argument in class, I think. If I have AG is equal to GA, if I just multiply this on both sides by A inverse, then that gives me that GA inverse is equal to A inverse G. And this holds for all G, this holds for all G, this holds for all G, that holds for all G. I mean, there's no condition on G in this calculation, therefore A inverse is in ZG. To be more pedantic, I should have every one of these. I should have for all G, for all G, for all G, for all, you know, a bunch of for all G's missing. Anyway, so therefore the center is a subgroup by the subgroup test. And then in terms of examples where the center is the whole group or the center is just one, you know, any abelian group will have the whole thing being the center, right? Because in an abelian group, every element commutes with every element. So any abelian example will do. Zn, n equals n greater than or equal to 2 will do. And mostly just because we haven't talked about Z1, I don't know what that means. It's probably just the 0 group, but I digress. And then this one was an example we worked out in here. It's in the book that the symmetric group of order n for n greater than or equal to 3 has just the identity in its center. Some people tried to use matrices for this, but that's not true. The center of the group of invertible matrices is actually constant multiples of the identity. See, if I have A times I times B times I, well, excuse me, if I have AI times the matrix M, that's equal to M times AI, and that's for all A not equal to 0. So certainly non-zero multiples of the identity matrix are in the center of the matrix group. So the center of the matrix group is not just the identity, it's more than that for the general linear group, which I had like 2 or 3 people try to use that as an example. It's not quite true. It's a good idea, it's a good guess, but not quite. And this was in the book, and also we worked it out in, I think, a help session. I worked it out. We looked at 3 elements, remember, KLM or something, and it's like a terrorist example. This is a pretty standard question, and it's important that you be able to work this out carefully. Many of you did. I think I had a lot of people do this pretty much correctly, and I was happy about that. There are many important parts here. Of course, noting that the identity is in the kernel, right? The homomorphism property makes the product of things in the kernel be in the kernel again, right? That the inverse property for homomorphisms. And you notice it's important that the inverse go out here. One of you wrote alpha inverse. That doesn't even have to exist. The inverse property says that alpha of x inverse is alpha of x. To be more pedantic, I mean, there's parentheses inverse. It could be that alpha itself is not invertible, right? If the kernel is not just the identity element, then alpha is not invertible because it's not injective. So it's a small point. Just one person did that. Anyway, again, by the subgroup test, the kernel is a subgroup. Now, of course, there is a pesky detail here, many of you maybe didn't even perceive as being part of the test, but it's an important part, which is that in order to work this problem, you needed to know what the kernel was, right? And I could tell from some solutions that you did not know, and you're trying to snowball me. And I almost fell for it, but then I looked at it and I realized, oh, it's not that this is a little bit wrong. This is them hiding the fact that they don't know what the kernel is. Aha, nice try. So I almost didn't see it, but I saw it. I personally got away with that on a qualifier. I forgot the distinction between, and this is pathetic. I mean, I just, the fact that I forgot this on the qualifier, there's no excuse. I should have done badly. But for some reason, I lost the distinction between, I want to say, solvable and simple, the algebras. I think that was it, which is just inexcusable. But I was able to work the problem using a high-powered theorem. Like I knew how to solve the theorem using that given problem on the qualifier with like a theorem. And then the professor must have thought I was trying to impress him by using the theorem to solve an elementary problem. He didn't realize that I was just hiding my ignorance by using a tool. It's like, yeah, your qualifier was really good. I'm like, thank you. Thank you very much. On the other hand, the thing I actually knew I did horrible on the qualifier for. And then like the first class, the next semester afterwards with my professor, he gave this like review of like very basic, that kind of math. And I knew in my heart that the reason we were getting that review was because of the horrible, horrible things I'd just done on the qualifier. And I was shamed. But I also deserved it. So anyway, me and my friend John both. But anyway, let's see here. You got no qualifiers to worry about, so just chill. Now this, nobody got this. Not a one of you. But this is actually, I believe, an example in the book. And I think I talked about it. I may not have in all the excitement leading up to the test. But yes, the sine function says it's 1 if it's an even permutation, and it's -1 if it's an odd permutation, right? So the kernel of the sine function is the alternating group. Consequently, it's a subgroup. Proved. Yes, no? So, and like at least 15 people told me why AN was a subgroup by the subgroup test. It's like, I have told you specifically without using the subgroup test theorem, I'm not going to give you partial credit on this kind of problem. Like, if I go to the trouble of specifically ruling out a method of solution, don't waste your time writing me a sentence like, you got to face the music. You didn't get it. Sorry, but anyway, maybe you'll get this on the final, right? I'm not guaranteeing it's on the final. I'm just saying. This was a homework problem, right? And I think we did this in class 2. I'm sorry, I did it on my back porch during party day, you may recall. Yes, maybe the lawnmower was going at this point, I don't know. But this is not, I mean, you can't go wrong here because the center of S3 is what? The identity, right? I mean, so like you pick any element of S3, you can find something else in S3 that doesn't commute with it. Is there any pair of permutations in S3 that do commute? I mean, of course, 1, 2 commutes with 1, 2, but.
I think I tried 1, 2 times 1, 2, 3, and then 1, 2, 3 times 1, 2, and it turned out to be the same.
Ah, okay. Cool. So it is possible. I guess I could hope you made a mistake, but that seems wrong. Let's see here. It would be my luck to pick the one possible one that doesn't give you a counterexample, you know. Now this one here is a fun problem, and this is conceptually challenging in the sense that it is a group with respect to matrix multiplication, right? So first of all, many of you proved that it was associative, and that's fine. But I would have been totally fine with you saying it's matrix multiplication, and we know matrix multiplication is associative. Okay? That's point one, number one. So it's an associative operation. If you calculate the product of A and, is that a B or is it a Pac-Man? I'm not sure. This is somewhere between B and Pac-Man. I guess B's grow up to be Pac-Man. Or is it the way around? Does a Pac-Man grow up to be B? I don't know. Let's see here. Pac-Man should grow up to be B's. Pac-Man should exist in childlike innocence. Right, yes, here. I mean, Pac-Man spends its whole day eating ghosts, right? It's got to be a kid. So this time, so it's an element of the same kind, right? G is closed. It's associative, and if you look at 1/2, I mean, once I write this, it was clear to me I should put a half, a half, a half, a half for the identity. You know, I mean, if I go back, as I said, readily seen from star, if I put in a half, I get AAA times that, it gives me a half. And the fact that it's an identity on both sides is something I should actually check. Oh, I'm sorry, it's actually clear from this calculation that it works on both sides, because I could either put half, a half, a half here, or I could put a half, a half, a half there. Either way, I get whatever's not the half, a half, a half as a result. So it's clear that that's the identity. And then to find the inverse, I just calculated it. So I want this times that is 1/2, 1/2, 1/2, 1/2. And so that tells me that 2AB is a half, so B has to be 1/4A. So there you go, that's the inverse. Which of course is not matrix inverse, right? Not the usual inverse of a matrix. This is the inverse relative to that group structure. It's not a subgroup. So many reasons. It doesn't have the identity, right? It doesn't have the identity of GL2. 1, 0, 0, 1's not in there, right? It doesn't have the same concept of inverse. So the structure is different. It's not the same group structure, right? Any other things you guys thought of? Right, and more to the point, it's not even a subset. That's the most important and first thing I should have said, is that G is not a subset of GL2, so it can't be a subgroup. Very good. Which is also the reason when you first see this homework question somewhere, it's very disturbing, right? Because it's like, how can it be a group under matrix multiplication? It's not even in the matrix group, right? Did I give this guys as a homework? No? Okay. Sometimes I do. Number 14, I think some people were successful. I acknowledge that this is challenging, and you didn't have a super long time to absorb it, but there should have been enough. And you guys set me on the straight and narrow after my initial wrong help session examples. Anyway, so 1, 2, 3, 4, 6, 5 is this one. You got to be careful this xy isn't what we want. We want yx squared, right? That's why we get 6 first. And then we get 5, because multiplying by x on the left, I have to move it past the y to get one of these elements. Now, if you can show me that what you have is the right thing for a different ordering of elements, I'll give you those points back. I haven't really thought through if there are other possible answers. It is conceivable that those of you who wrote 1, 2, 3, 4, 5, 6, that is correct with respect to some numbering of the group. But I'm not going to go sort through that and figure out if you're right or it's not. I just think that you just wrote down 4, 5, 6 without thinking. So I'm not going to think for you. If you want to think through it and convince yourself that it's true and come argue with me for those points back, go for it. And this one's 1, 4, 2, 5, 3, 6, yeah. Okay, so now that's it, because the isomorphic group needs 6 things, right? This has order 3, this has order 2, because the least common multiple, the disjoint cycle decomposition, right? Disjoint cycle factorizations, and least common multiple is 3, least common multiple is 2, because 2, 2, 2 is 2, 3, 3 is, anyway. And so if I've got an element of order 2 and an element of order 3, then I put them together, I get 6 things. Because there's no way underpowering either one of these gives each other, right? No matter how many times you take a power, you can't change a 3 cycle to a you know, this kind of, these cycle types are not connected under powering. Anyway, admittedly, I haven't entirely proved that that's G bar, but there it is. The isomorphism with S3, I think the easiest way to do it is just to notice, I mean, of course, you could write down the KLA table for both and go, hey, look, they're the same. This seems very, very, very difficult way to earn 6 points on the test, right? I mean, it's a lot of writing. And they're not entirely easy KLA tables to construct either, are they? Because this is not a abelian group. You actually have to think about it. So the fastest and most efficient way to understand S3 or D3 is generators and relations. And so for the isomorphic, so I have this, let's see here, this, I'm sorry, I've forgotten my question at this point. I'm sorry, guys. If I'm just showing isomorphism of S3, oh man, I really should have asked, is G bar isomorphic to, no, I'm sorry, I did want this. I guess you could think about this question without connection to the part A. I'm just thinking of it in connection to part A. Okay, so with the connection to part A, and I guess that makes it more complicated than it needs to be, but basically I have this A, I have this B in the isomorphic copy of D3, and it satisfies the relation ABA is B, right? And A has order 3, B has order 2, so if you look at it, G bar has this structure in terms of generators and relations, but you can recognize this is just S3 in terms of generators and relations. So if I send A to sigma and if I send B to tau, as in like the sigma and tau in the book that generate S3, you know, then that will extend to an isomorphism because it's sending generators in the same relations in both groups. And so that shows you that G bar is isomorphic to S3, but of course G bar is isomorphic to D3 by construction. And so that means S3 is isomorphic to D3. As I think about it more right now, you could just prove this directly by just, I mean, all you really need to do for D3 is take xy such that what? X cubed is E, y squared is E, right? And how did we present the relation? X, I think I told you xy is equal to what was it? Yx inverse. So, I mean, honestly, you could just go, oh, okay, so x, y, x is equal to y again. And then directly from this generator's relation presentation of D3, sending x to A, sending x to sigma and y to tau gives you the isomorphism of D3 and S3. I was just seeing it through the lens of my KLA representation because that's what I was thinking about. But admittedly, that's more complicated than it needs to be. I will admit. Now, I will tell you where this problem came from. I originally had something else, and then Dr. Smith's like, no. You should ask them, is D4 isomorphic to S4? And I thought, oh, yeah, that's better. Because it's very tempting, since I just showed you that D3 is isomorphic to S3, right? You argued that in part B. So I figured I could fish some of you into saying that without thinking, indeed, it was the case. Sorry, I shouldn't be happy about your suffering. It's a character flaw. But this is obviously not the case, because S4 has 24 things in it. D4 has got 8. These are not isomorphic. Yep. So I didn't write the solution out for this one because I'd like you guys to think about it. So, I mean, I'll talk about it. To prove part A, that's just a subgroup test. I mean, this is a special case of the homework problem you guys worked with the J in it. Basically, this is just J I called it eta instead of j. This is not the j in your homework. In your homework, you have like a g sub j. Remember that problem? I think I had this in your homework. It has is a g sub j is a in Rn by n such that was it A transpose JA equals to J again? So show that that's a subgroup of GLNR. And I wanted you to see if you put J equals to the identity, you get the orthogonal group, right? Sounding familiar? No. So this is really just a special case of that. Part A is a special case of your homework. It's not easy, but it's not that hard. And then here, this is just a calculation. C of j is the centralizer of j, so you're looking for all matrices which commute with 0, 1, 1, 0. If you work that out, you should get that it works out to ABBA. ABBA, it's really nice. And then intersecting that with SL2R means that a squared minus b squared has to be 1. And then the isomorphism from that to that, I'll let you think about. Nobody got part C. One person got almost got part C. He understood what he had to do for part C, but he couldn't quite see it. Sorry, it's awful. Other questions? I think next time I'm going to give you guys a 2-page test, so I only have 2 pages to grade, because you guys actually wrote stuff on like 3 or 4 pages. It's like a lot to grade. And no one's dropping the class either, so it's not helping me in that regard. I mean, if like 10 people drop the class, then I could keep the length of the test where it is, right? But no. I think I will give a slightly shorter test next time, but I think if you look at where you used your time, you realize that you could have done this if you calculated certain things differently. It's still tough. I mean, it's not an easy test. I don't think. No one will argue with me about that, right? The test was too easy. Make a real test next time. No? Too soon? Oh. So, if you got questions about the homework, I got a couple minutes. Not yet? No? I didn't think so. Well, I guess that's it for today then. Thanks, guys.